A warship does not become dangerous only when a guided round leaves the rail. It becomes dangerous much earlier. In the instant a distant signal, a heat bloom, a radar flicker, a wake line, a radio whisper, or a machine-classified shape is turned into certainty. That is the real shock of modern conflict. The sensor is no longer just the eye of the force, it is the hand that directs the outcome. In a combat web, the side that sees first understands first, and hands that understanding to the right unit first can pressure an opponent before anyone has even heard the first impact. This is Battletech Declassified. Modern Warfare Explained. Tonight, we are not talking about one drone, one ship, or one guided round. We are talking about the invisible nervous system that turns scattered sensors into a force multiplier in their own right. By the end of this documentary, you will understand why a radar can matter more than a gun, why a drone camera can matter more than a ship's steel, and why the future contest is not just about who has the biggest arsenal, but who can turn fragments of information into a coordinated response faster than the other side can think. For a long time, militaries liked the phrase engagement chain. It sounded neat, mechanical, almost comforting. Find, fix, track, target, respond, assess. One link after another, like a row of dominoes. But modern conflict rarely behaves like a polite row of dominoes. It behaves more like a spider web in a storm, strands shaking, reconnecting, rerouting, absorbing damage, and still catching whatever drifts into it. That is why the combat web matters. It is not one straight path from sensor to response. It is many possible paths, all competing to turn awareness into effect. Think of the difference like this. An engagement chain is one road from your house to school. If that road is blocked, you are late. A combat web is an entire city map, back streets, bridges, alleyways, tram lines, and bike paths. If one route closes, another opens. In military terms, a satellite can cue a drone. The drone can hand off to a ship. The ship can push data to an aircraft, and the aircraft can guide an action started by someone else entirely. The power is not any single platform. The power is that the web gives commanders options, and options are what turn raw sensing into practical force. That sounds abstract until you see what it really means. In the old model, a platform often had to do everything itself. It had to detect the threat, identify it, track it, and respond with its own systems. That made every ship, jet, or battery something like a lone hunter carrying its own flashlight, map, and rifle. Powerful, yes, but limited by what it could personally see. In a combat web, the flashlight belongs to everyone. One platform can sense, another can decide, a third can launch, and a fourth can assess the result and redirect the next move. This changes the meaning of range. A guided round does not only reach as far as its motor can fly, it reaches as far as the web can see and maintain confidence. A sensor at the edge of the battle space can extend the reach of a launch unit hundreds of miles away. That is why sensors begin to behave like force tools. They are not made of steel and explosive filler, but they create the conditions that make an effect possible, and they do it by collapsing distance, time, and uncertainty all at once. But seeing something is not the same as knowing what it is. That is where people get fooled by the word sensor. It sounds clean, like a camera catching a perfect picture. In reality, sensors usually give you fragments. A radar return may tell you there is something moving, not exactly what it is. An infrared sensor may reveal heat, not intention. A passive electronic sensor may hear emissions, but not show the full shape behind them. A combat web becomes decisive only when it turns these fragments into a track good enough to act on. Imagine hearing footsteps upstairs at night. You know something is there. But is it a burglar, a family member, or the cat doing something illegal with a plant pot again? Acting too early is risky. Acting too late is worse. Modern battle managers face the same problem, only with aircraft, submarines, drones, and incoming systems, instead of creaky floorboards. The job of the combat web is to stack clues until uncertainty shrinks enough that action becomes justified, fast, and effective. That means the real ammunition is not just hardware. It is confidence. Confidence starts with diversity. If one radar sees a contact, that is useful. If a radar sees it, an electronic support measure hears it, a space-based sensor notices activity in the same area, and a forward drone catches a matching silhouette, the picture hardens. Suddenly, the target is less like a rumor and more like a person standing under 4 street lamps at once. The web becomes strong because different sensors see the world differently, and opposing forces have a much harder time fooling all of them at the same time. This is why modern forces obsess over fusion. They are not trying to collect more information just because information looks impressive in a briefing. They are trying to make deception more expensive. If an opponent spoofs radar, passive sensors may still betray him. If he goes quiet electronically, infrared may still catch heat. If clouds block one view, another angle may remain open. A combat web is powerful, not simply because it gathers data, but because it layers perspectives until the target runs out of hiding places. Passive sensors deserve special attention because they reveal one of the most important tricks in modern conflict. The quietest side can often be the most dangerous. Radar shouts. Passive sensors listen. In a contested environment, shouting can get you exposed. Listening lets you map the room without turning the lights on. Electronic support measures, acoustic systems, infrared search and track, and other passive tools let forces build a picture while keeping their own signature lower. That matters because emissions are invitations. The moment a radar goes active, it can announce position, pattern, and purpose to anyone paying attention. In a combat web, a force can leave some nodes silent while others listen, classify, and pass the information along. A launch unit may act without ever having illuminated the target itself. That is a huge shift. It means a platform can remain harder to find while still remaining dangerous. The sensor, elsewhere in the web, has effectively become part of the response system. Now flip the picture. Sometimes active sensors are still necessary, and when used well, they are not just eyes. They are bait, probe, and timing device all at once. A radar burst at the right moment can provoke enemy reactions. A ship turns, a jammer activates, a seeker wakes up, a decoy blooms. Suddenly, the other side reveals more than it meant to. In that sense, a sensor can pressure the opponent not by causing direct damage, but by forcing him to expose himself. It is like tapping the wall in a dark house and listening for what scurries. The tap is small, but the movement it triggers can give everything away. Combat webs thrive on these forced reveals. A brief active search may not deliver the final effect itself, but it can sharpen the picture, confirm identity, or trigger exactly the emission the rest of the network was waiting to catch. This is why the line between sensing and responding keeps fading. Modern sensors do not just observe the battle space, they shape it. Once a target is detected, the next question is ownership. Who has the best track? Who has the authority? Who has the response system with the best chance of success? In a combat web, this is less like one cowboy quick drawing and more like an orchestra trying not to have 3 drummers smash the same note while the violinist misses her cue. The value of the web comes from choosing the right response unit, not merely the nearest one. An aircraft overhead might see the target first, but a destroyer may have the better guided round. A coastal battery may be hidden and better placed. A drone may maintain contact longer. An aircraft may be low on munitions and should remain as a sensor rather than become a response unit. The web has to weigh all of this in real time. When it does, the sensor becomes decisive because it does not just discover the target, it helps assign the most efficient form of force to that target. This is where geometry enters the story, and geometry is one of the quiet kings of conflict. Angles decide what can be seen, what can be hidden, and what can be acted on. A ship behind the curve of the Earth cannot be engaged by a long-range system that has no one to guide it to the right patch of ocean. A low-flying aircraft may vanish behind terrain. A submarine may hear what nobody else can hear, but only from certain positions. The combat web works by stitching together these angles until the opponent is boxed in by viewpoints. Picture a football match viewed from one cheap seat behind a pillar. You see movement, but not the whole play. Now add cameras from the roof, behind the goal, on the sideline, and on a player's chest. Suddenly, the game becomes obvious. That is what distributed sensing does. It replaces a partial picture with a layered one. When the opponent is seen from multiple geometries, escape routes shrink. The sensor is no longer just telling you that something exists. It is telling you where, how, and from which direction a response should arrive. Forward scouts make this even more dangerous. Small drones, Unmanned surface vessels, forward aircraft, special operations teams, and remote sensing nodes push the web outward like fingertips reaching into darkness. They do not need to carry the heaviest systems themselves. Their value lies in being close enough, quiet enough, or expendable enough to keep contact with the target while others remain farther back. This is one of the deepest logic shifts in modern conflict. The most important platform in a given moment may not be the most expensive one. It may be the cheap scout that survives long enough to maintain a track for 20 extra seconds. Those 20 seconds can be the difference between a target slipping away and a distant launch unit achieving its effect. In that sense, the scout's sensor has become part of the response mechanism. The guided round may get the cinematic credit, but the sensor wrote the ending. Naval conflict makes this especially clear because ships are both powerful and vulnerable. A major surface combatant carries formidable sensors and strong response systems, but it is also a large signature in a world increasingly crowded with satellites, drones, submarines, and long-range systems. If that ship has to expose itself to find every threat personally, it risks becoming both hunter and billboard. Combat webs let the ship remain a node in a larger pattern rather than the lonely center of it. That means a warship can receive targeting quality cues from elsewhere and act with less self-exposure. It may hold response until another sensor confirms the track. It may launch based on off-board data. It may contribute its own radar only in short, controlled bursts, or reserve it for terminal moments. This makes the sensor picture itself a protective tool. The web lets the ship operate without constantly sticking its head above the trench. And in a long-range threat environment, that kind of discipline is not polite. It is survival. Aircraft add speed and altitude to the web. A plane sees farther because it lives above the clutter that limits surface sensors. It can move faster to close gaps, reposition to better geometry, or relay information between nodes that cannot talk directly. In practical terms, that makes airborne sensors some of the most valuable threads in the web. They are not just lookout towers. They are moving bridges. And because they move, they can create temporary windows of advantage. An aircraft can appear on one flank, light up a sector, classify tracks, and vanish or hand off the track before the opposing side fully reacts. It can spot a target that a ship could not see because of sea state or horizon limits. It can also serve as a tactical translator, converting what one part of the force knows into something another part can use. That is what makes the sensor tool-like in a force sense. It extends reach, creates opportunity, and decides timing. Space pushes this logic even farther. Satellites, or more broadly space-based sensing, do not operate like ships or aircraft. They do not dodge well. They do not improvise like humans. But they offer something uniquely valuable: persistence and scale. They watch broad areas, revisit patterns, flag anomalies, and build the strategic backdrop against which tactical nodes can act. They are like the scoreboard camera, the traffic helicopter, and the neighborhood gossip all rolled into one very expensive machine. That does not mean a satellite alone gives you a perfect response quality picture every time. Public discussion often blurs the difference between surveillance and immediate action quality targeting. The important point is that space sensors can narrow the search, reveal movement patterns, and cue lower-level assets to look in the right place at the right time. In combat web terms, that is enough to matter enormously. A broad stare from above can turn a blind hunt into a guided ambush, and that makes sensing itself part of the response architecture. Below the surface, the undersea picture is different, slower, quieter, and often cruelly uncertain. Acoustic sensing, wake detection, underwater drones, fixed arrays, maritime patrol aircraft, and shipborne sonars all contribute pieces, but the ocean is a liar. It bends sound, hides signatures, and turns every confident claim into a question mark unless multiple clues line up. That is exactly why the combat web concept matters so much underwater. One sensor may hear a possible contact, another confirms a pattern, a third refines location enough for further action. Just as important, the web can keep track custody even when one node loses it. Instead of treating contact as a fragile thread that snaps the moment one listener goes deaf, the web keeps weaving. In undersea operations, that persistence is everything. The torpedo may be the visible end of the story, But the real tool was the network that kept the target from dissolving back into uncertainty. Land-based launch units also changed the balance. Coastal long-range batteries, dispersed ground units, and hidden fire systems can become maritime threats or air defense contributors when fed by the right sensors. This is one of the big strategic headaches for any navy approaching a hostile coastline. The response unit may be hidden inland, mobile, and hard to disable. The sensor that cues it might be somewhere else entirely. That means the battle space stretches in awkward ways. A ship may think in terms of sea control, but now land, air, cyber, and space all help determine whether it can survive offshore. A sensor on a hill, a drone over a bay, and a remote command node inland can combine to make a coastal battery dangerous far beyond what its local awareness would allow. In that moment, the web has operationalized geography itself. The shoreline becomes less a border and more a trap. Silence, then, is not absence. In a combat web, silence can be a posture. Emission control is often described like discipline, and it is, but it is also a strategic choice about who in the network will speak and who will remain quiet. Some nodes expose themselves so others do not have to. Some stay silent until the last useful moment. The web distributes risk as much as it distributes information. This is easy to miss if you imagine every platform operating like a movie hero who insists on doing everything personally. Real effectiveness often comes from restraint. A ship may withhold radar because a drone can provide enough warning. An aircraft may remain passive because another aircraft has already painted the picture. A battery may wait in complete silence for a handoff. That restraint can be decisive because it preserves surprise. The sensor, elsewhere in the web, does the dangerous talking so the launch unit can remain a hidden fist. Machine speed is where this all becomes uncomfortable. Humans are still central, especially when it comes to judgment, rules of engagement, and the seriousness of high-consequence decisions. But raw data movement, track correlation, and recommendation cycles increasingly happen at speeds that make old command rhythms feel like trying to swat flies with a cathedral. If the web cannot process fast enough, its elegant structure becomes a museum piece. This is why modern command systems chase lower latency, better fusion, and more automated assistance. Not because officers want robots to feel important, but because there is simply too much information for unaided humans to sort in time. The danger, of course, is that speed can seduce. A fast wrong answer is not wisdom. It is an expedited mistake. So the practical value of a combat web depends on balancing machine speed processing with human-level judgment, enough velocity to act first, enough skepticism not to act on a mirage. Latency is the villain nobody cheers for, but it kills more opportunities than many people realize. A perfect track delivered too late is like an ambulance arriving after the fire brigade has already held the funeral. Targets move, jammers interfere, data gets stale, permissions lag, connections drop. In a web, time is not a background detail. Time is part of the effect. The public often imagines a force, sees a target, presses a button, and something happens moments later. In reality, every delay corrodes the usefulness of the picture. A target that was real 30 seconds ago may now be somewhere else. A launch based on stale data may fly faithfully toward irrelevance. That is why the best combat webs are designed not merely to gather information, but to preserve its freshness long enough to matter. Speed is not glamorous here. It is simply the tax you must beat before the other side turns your beautiful data into old news. Now we get to the darker side, poisoned tracks. If sensors can become force multipliers, then manipulated sensors can become friendly fire against your own decision-making. An opponent can jam, spoof, decoy, saturate, mimic, or overload the web with false signals. The aim is not always to make you blind. Sometimes it is better to make you see too much and trust the wrong thing. That is a nasty truth of modern contest. Confusion can be more useful than silence. A fake track can pull a launch unit off station. A decoy can burn a valuable round. A spoofed emitter can make you reveal your own sensors. A flood of small signatures can bury the one that matters. This is why sensor confidence scoring, cross-checking, and fusion discipline matters so much. In a combat web, You are not just trying to see, you are trying to see honestly, and honesty in a contested space is expensive. Confidence scoring sounds dry, but it is one of the great life or death filters of the web. Not all tracks are equal. Some are solid, some are probable, some are rumor dressed like fact. A mature combat web treats tracks with layers of confidence, source quality, freshness, and corroboration. It does not flatten everything into one glowing icon that looks equally trustworthy. Think of it like a courtroom instead of a rumor mill. One witness is useful. 3 independent witnesses, video, and fingerprints are stronger. Likewise, a track from a single noisy sensor may guide attention, but not authorize decisive action. A track from several aligned sources may. The web becomes dangerous because it formalizes doubt without being paralyzed by it. Done well, that makes sensors more than observers. It makes them weighted votes in a high-consequence decision system. So where does the human sit in all this? That question haunts every discussion of combat webs, because the more connected and accelerated the system becomes, the more tempting it is to push people out of the loop. But conflict is not a spreadsheet. It is moral, political, and full of edge cases that punish overconfidence. Humans remain essential not because machines are useless, but because consequences are human even when data is digital. The real aim is usually not full removal of people, but smarter placement of them. Let machines fuse, compare, recommend, and prioritize. Let humans define intent, set constraints, approve major actions where required, and intervene when the picture smells wrong. The best combat web is not a robot empire. It is a disciplined partnership where software handles the flood and humans handle the meaning. That matters because a sensor can only become a legitimate force multiplier if the decision around it remains accountable. One reason combat webs outperform engagement chains is resilience under damage. A chain breaks, a web frays, then reroutes. Lose one node, and the system can still function if enough alternate paths remain. That sounds simple, but it changes wartime behavior dramatically. Forces can distribute sensors, launch units, and command elements because they no longer assume every action depends on one golden platform staying alive. This has huge consequences for how an opposing force must respond. Instead of taking down one obvious centerpiece, it must suppress many smaller contributors across different domains. That is harder, more expensive, and often slower. The web does not promise invincibility. Nothing honest should, but it raises the amount of damage the other side must do before your awareness truly collapses. In practice, that means every surviving sensor remains a possible path to a response, and that lingering danger itself becomes a form of deterrence. Redundancy, though, is not duplication for its own sake. It is functional overlap. 2 sensors that fail in the same way are not true redundancy. They are twins who both forget the house key. Effective combat webs use diversity in platform type, sensing method, and geography so that the same trick does not blind everything at once. A radar and another radar may both suffer under the same jamming conditions. A radar plus passive electronic sensing plus infrared plus visual confirmation from a drone is a tougher bundle to defeat. Redundancy also includes communication paths, power, timing references, and authority structures. If one data link dies, another route should carry the essentials. If one node is cut off, local units should still have fallback behavior. This is where combat webs stop being buzzwords and start being engineering. Practical effect depends on boring robustness. Electronic warfare turns this contest into something close to a haunted house. Signals appear, vanish, distort, multiply, and lie. In that environment, the most valuable sensor may be the one that reveals the opponent's attempt to manipulate the picture. A jammer is not just a problem, it is also evidence. It tells you someone cares about this patch of spectrum right now, for reasons that may expose their priorities. This leads to one of the more elegant ideas in the modern battle space. You can use the other side's attempts to hide as part of the track itself. A sudden burst of jamming, a reactive maneuver, or a pattern of emission control can all feed the web's understanding. In other words, the opponent's panic becomes data. That does not make jamming harmless. Far from it. But it shows why sensing is now active, adversarial, and tool-like. You do not just observe the opponent. You provoke him into revealing pieces of himself. Decoys push the logic even further. because they aim to trigger the web's instincts. A good decoy does not need to be perfect. It only needs to be believable long enough, in the right context, to steal attention, burn resources, or shift positioning. That means the battle is increasingly fought in the mind of the network, not just in the air or at sea. This is why combat webs need memory and behavior analysis, not just snapshot detection. Does this contact move like the platform it claims to be? Does it emit like one? Does it fit prior patterns? Does it make tactical sense? The better the web is at asking those questions, the harder it is to trick. But when it fails, the consequences are severe. A decoy can turn a sensor from force multiplier to liability. Modern conflict in that sense is a duel over which side can make the other side's eyes betray them. At the center of all this sits battle management, the conductor of the orchestra. This does not always mean one big glowing command room issuing orders like a villain in a submarine movie. In fact, over-centralization can be a weakness. The important thing is that someone or several linked decision nodes can prioritize, arbitrate, and align action across the web, so that sensors and response units are not operating like brilliant strangers at the same dinner party. The conductor decides what matters now, which track is urgent, which unit should hold, which sensor should illuminate, which unit should stay silent, which risk is acceptable. In a sense, battle management operationalizes attention. It tells the force what to care about and when. That makes it one of the most valuable and vulnerable pieces of the entire system. If the conductor collapses, the orchestra may still play, but the music gets dangerous fast. Mission Command helps solve that. If local commanders understand the broader intent, the web can survive partial blindness and still act coherently. Instead of waiting for every answer from above, units know the purpose of the fight, the boundaries of action, and the priorities for handoff or response. This is not just old military wisdom wearing new digital clothes. It is a practical requirement when connectivity may be contested and timing punishes hesitation. A robust combat web therefore depends on doctrine as much as hardware. The data can be brilliant, but if the people using it freeze when one link goes down, the whole structure becomes fragile theater. Shared understanding lets units improvise without unraveling the common plan. In plain language, the web needs smart habits, not just smart software. Otherwise, 1,000 sensors still leave you standing there like someone with 20 cooking apps and no idea how to boil an egg. Logistics rarely gets invited to the glamorous part of these discussions, which is unfair because the web runs on hidden sustainment as much as it does on dazzling electronics. Sensors need power. Data links need maintenance. Spare parts matter. Software needs updates. Calibration drifts. Operators need training. Antennas break. Batteries die. A combat web that cannot be sustained is just a very expensive rumor. This is especially important in protracted conflict. It is one thing to demonstrate a connected response architecture during a clean exercise with coffee, stable weather, and technicians sleeping indoors. It is another to keep that architecture alive through attrition, weather, deception, disrupted supply lines, and the general rudeness of conflict. The side that sustains the web longer often gains a compounded advantage. Every surviving sensor still contributes. Every repaired node reopens pathways. In a long contest, endurance operationalizes information. Rules of engagement also sit right in the middle of the problem. A sensor may reveal a contact, but lawful and politically acceptable action still depends on identification, context, and command thresholds. This matters because the cleaner the network becomes, the stronger the temptation to believe the picture is morally simpler than it really is. It rarely is. Positive identification can require more than a machine correlation or a suspicious track history. Civilian traffic, neutral actors, deceptive signatures, and ambiguous behavior all complicate the path from track to action. That does not weaken the combat web concept. It grounds it. The sensor can be force-like, yes, but only inside a framework that separates hostile from non-hostile with sufficient care. Otherwise, the web becomes not a precision instrument, but a fast machine for strategic self-harm. Blue-on-blue risk is the nightmare that lurks behind every conversation about speed. The same network that helps you see the opponent must also help you not act against your own people. Friendly force tracking, identification systems, data hygiene, timing discipline, and clear authority rules all exist. partly because modern webs compress action so quickly that mistakes can become irreversible before anyone finishes saying, "Wait a second." This is another reason sensor quality matters so much. A force that cannot distinguish friend, foe, neutral, and unknown is not highly networked. It is merely highly dangerous to itself. Mature combat webs treat self-awareness as part of effectiveness, because preserving your own force keeps the web alive and keeps future options open. It is an unromantic truth, but perhaps the most important one. Precision begins with not harming your own side. Cheap, attritable drones are giving combat webs more fingers. They can scout ahead, relay signals, absorb attention, act as decoys, or simply be close enough to maintain line of sight or emissions contact where larger platforms would be too valuable to risk. That means the cost curve of sensing is changing. You no longer need every thread in the web to be exquisite. Some just need to be present. This matters because quantity has a quality of its own when distributed properly. A cluster of small sensing nodes can fill gaps, complicate enemy targeting, and keep track continuity even as some are lost. The expensive launch unit behind them now operates with a screen of disposable eyes. Again, the sensor becomes force-like because it lets high-end capability act through low-cost presence. The chessboard thickens. Suddenly, what looked like a camera drone is actually part of a long-range response system's extended nervous system. Counter-space measures, cyber pressure, and communications disruption remind us that the web itself can be targeted like infrastructure. If your force depends too heavily on perfect connectivity, the other side will not try to win your game. It will try to unplug the console. That means designing for degraded operations is not pessimism. It is realism. A credible combat web must therefore have graceful failure modes. If satellite support weakens, local airborne sensors should still function. If long-haul links are jammed, line-of-sight relays and pre-planned behaviors should carry the essentials. If central fusion becomes patchy, local commanders must still operate with partial but trustworthy pictures. The most dangerous web is not the one that looks godlike in peacetime. It is the one that keeps enough truth alive when half the ceiling caves in. Artificial intelligence is often sold like a magic wand in these conversations, which should make anyone suspicious immediately. AI will not remove fog, fear, friction, or politics from conflict. But it can help in the places where modern combat webs genuinely hurt, filtering clutter, ranking anomalies, correlating signals across domains, and suggesting pairings between tracks and response units faster than a human staff can manage alone. The promise, then, is not all-knowing machine conflict. The promise is narrower and more useful. AI can help reduce the cognitive tax of the web. It can sort the inbox before the commander reads it. It can flag the track that does not fit. It can notice patterns across weeks of surveillance that humans might miss. Used well, that makes sensors sharper force multipliers because it turns more raw sensing into usable meaning. Used badly, it simply automates delusion with better typography. There is also a deeper strategic implication here. Combat webs reward integration more than isolated excellence. A force can have brilliant guided rounds, excellent aircraft, and advanced radars, but if those things do not connect, trust, and hand off effectively, they behave like talented strangers forced into a three-legged race. Meanwhile, a less glamorous force, with tighter integration, can outperform its individual platform quality. That is why modern military competition increasingly looks like a contest of systems rather than shiny objects. Buyers and planners still love the dramatic platform reveal. A new ship, a new stealth jet, a new long-range round. But the harder question is always, how does it join the web? How does it sense? How does it receive? How does it pass? How does it survive under degradation? The sensor becomes a force multiplier, not in isolation, but because the system around it knows what to do with what it sees. This has changed deterrence as well. An opposing force does not only fear your visible response systems, it fears your ability to find, classify, and coordinate against it from multiple directions. It fears that the moment it moves, emits, or concentrates force, your web will notice and offer several unpleasant ways to respond. In that sense, sensing itself becomes a deterrent act. Deterrence used to lean heavily on obvious mass. Fleets, garrisons, bomber numbers, round counts. Those still matter. But now invisible architecture matters too. A force that can keep coherent awareness across domains imposes caution before action even begins. The opponent must assume that concealment is thinner than it looks, that silence may still be heard, and that exposure may summon responses from places he is not currently watching. A good combat web, therefore, pressures not only by what it can do, but by what it can know. The economics of this are brutal and fascinating. If a relatively cheap sensor node can help guide a much more expensive response system efficiently, it can improve the whole exchange ratio of the contest. At the same time, if your opponent can knock out your sensing cheaply, your expensive launch units become clumsier, shorter ranged, and easier to neutralize. The value battle shifts upstream, from just ammunition stocks to information pathways. This means cheap sensors, resilient comms, and distributed fusion may sometimes generate more practical combat value than adding one more exquisite platform with exquisite maintenance needs. That does not make high-end systems obsolete. It means they depend more than ever on the quality of the web around them. A sports car without roads is just a very proud sculpture. In conflict, premium launch units without surviving sensors are much the same. History offers a useful contrast. Earlier eras often concentrated sensing and responding in the same place because technology gave them little choice. A warship saw with its own optics, ranged with its own instruments, and used its own guns. Even later, many air and naval platforms still thought in largely self-contained loops. The modern shift is not merely longer range, it is externalized awareness. That is a profound change in battlefield identity. Platforms increasingly matter not just for what they carry, but for what role they play in the web at a given moment. The same aircraft may be sensor, relay, decoy, launch unit, or command enhancer depending on context. The same drone may scout one minute and act as bait the next. The battlefield starts to behave less like a set of duels and more like a living organism, senses, nerves, muscles, and reflexes spread across many bodies. And that organism can be surprisingly fragile if trust collapses. Trust between machines, between units, between commanders, and between what the system says and what operators believe. Without trust, data stalls. People hoard tracks. Units duplicate effort. Launch units hesitate. Sensors overexpose to compensate. The web turns from a nervous system into office politics with antennas. So, the hidden foundation of combat webs is not just technology. It is credibility. Operators must believe the sources. Commanders must believe the handoffs. Units must believe that sharing information will help rather than expose them unnecessarily. Building that trust takes exercises, common standards, repeated procedures, and hard lessons learned before conflict. A sensor becomes a force multiplier only when others trust what it says enough to act on it. All of this brings us to the most important insight. Combat webs do not turn sensors into force multipliers because sensors suddenly start exploding. They do it because they make sensing decisive in the application of force. The one who keeps the cleaner, faster, more resilient picture can place action with more precision, more surprise, and less wasted effort. The hardware delivers the visible effect, but the web decides where that effect becomes possible. That is why future conflict will not be won by counting launchers alone. It will be shaped by which side can preserve truthful awareness under pressure, which side can reroute around disruption, and which side can transform fragments into action without sliding into panic or illusion. In a combat web, the sensor is not backstage support. It is center stage, quietly deciding whose rounds matter, whose ships survive, and whose mistakes become headlines. So when people ask what modern conflict is becoming, the clearest answer may be this. It is becoming a contest over who can connect perception to force more intelligently than the other side. Not who can merely see more, but who can see in a way that survives friction. Not who can merely respond farther, but who can give those responses a living, updated understanding of where the opponent truly is. Not who has the loudest radar or biggest fleet, but who can make many imperfect eyes behave like one thinking system. That is the final truth of the combat web. It does not replace guided rounds, ships, aircraft, submarines, or troops. It gives them a shared brainstem. It lets a distant drone matter to a hidden battery, lets a passive sensor protect an exposed launch unit, lets a satellite narrow a search, lets a ship act without shouting, and lets information arrive as organized effect instead of scattered noise. In the conflicts now taking shape, that may be the difference between having capability and actually being ready.